clear? Please raise your hand. Right, so thank you. Yeah, sorry for the last minute calling for this online class. Right. So because tomorrow tomorrow morning actually I'm not sure what time I free or not, because I sending my son go for the registration university tomorrow. Right. So anyway, tonight I try to finish early lah. Right. Okay, actually I just want to finish our chapter 6. Okay, so in our previous lesson we already basically we done our first subtopics already for the radioactive on the half-life. Okay, so this question I think you still remember is SPN 2022, which is the last year. The question have problems on the scale for the y-axis, which is the activities count per minutes here, right? Okay, so as you can see, that's the scale actually is not the linear scale, so is the concept's wrong already. Right, if you plot the scale for this y-axis like this, okay, so according to the concept, by right, with this 1000 on top here, which is as the beginning for the 100% here, beginning here, this is the one where the time is 0 here, so that is our beginning time, beginning count per minutes here. All right. Okay, so with that, when you based on this height, when the moment we divided 2, means that here, which is the 50%. So by right, it should become to 500 from 1000. Okay, decrease to 500. But as you can see, the 500 is here. All right, so that's why the scale itself actually is wrong already. All right, the scale itself, according to the ratio of the length, is wrong already. And then after that, by right here is a 25%. So it should be showing the reading here is a 250. So only with that, when you see that when you get the half right here, 1000 decrease to 500, which is this half right. According to this, you will get the time is 8 minutes here, right? And after that, from 500, another half right, 500 reduce half, become 250. There is another half right. So according to this, when you draw a line here, it will come to the reading 16. So it means that it will get the constant half right. So this is one half right. This is another one half right. So from here, no matter how you do, you will still get the result half right will be equal to 8 minutes. All right, according to original correct questions, right? So even if you don't trying to start from 1000, so let's say according to this by right, the readings here, this one it should be 750 according to ratio of the length, According to this, when you take 750 as a starting readings here, all right, you should get the reading something is around here, right? And after that, from the 750, after one half right, it will become 375, right? 375 divided 2, 750 divided 2, you become 375. So according to the correct ratio, when you get the 375, I think it will be around here, center here, 375 here. So in that case, you will get another readings here. This reading, somehow the interval of these two reading, it will be showing 8 minutes also. It will be showing 8 minutes also, no matter how. Right? No matter how, it was still showing the 8 minutes also. Even you are not trying to get from the 1000. Because that is a concept of half right. As long as any initial reading as your first starting reference, after the one constant period of time, the initial reading, it will decrease half. It will decay half and then remaining half. So That is a concept half-life. So that's why we have this decay curve. But once a scale label wrongly like this, if you follow the readings, you will get different result. You will get different result if you follow this scale for the last year SPM. So I don't know how is the teacher discussed with you guys for those going to the STAR SPM program. The STAR SPM program, they give you the last year SPM questions, right? Did they discuss about these questions or not? For those going the STAR SPM program today, they discuss this question or not? Anyone? For those going to the STAR program, or went to the STAR program once, they don't discuss the questions. Huh? Then they give you all the question paper, what they discuss. They don't really go through question by questions. Yeah, wasting time on like that. Okay, so you see, if you follow this from the 1000 beginning, after one half right, it will go through 500. So this is one half right. Then another from 500 go to the next one, it will be 250. So this is another half right, 500 to 250. So if you don't care, you just take from 1000 to 500, then you will get the result. Okay, not exactly 4 minutes. It will be based on the ratio. Based on the ratio, you will study that. Actually, this is the graph paper. They will see the grid line because this one scan the grids behind is missing, no clear already. So actually, you will get the reading very close to the 4 minutes. Then if you take from here, and after you go to the second reading, 350, you may show here's the edge. So the student will be use the edge minus this one to get the half-life for that correct the understand students lah. Okay. But what I worry is if the student try to make the correction by themselves, I don't know how they consider about the answer. Because this part is they cover up their mistake. So the marking teacher, it won't tell us. All right. So somehow with the previous experience, because the year 2021, also there's one question is wrong about the chapter 7 quantum physics. The question also wrong. So then I asked my friend. My friend told me that the questions that accept any logical answer. So it means that basically whatever answer you give, as long as it's logic, then they accept. So the one later when we discuss the quantum physics, I will tell you why. Okay. So it really happens again for this coming SPM. As I mentioned before, you do what you can do. All right. Based on your concept, you do what you can do. So the safer one, like the case like this, you follow lah. 1000, one half-life go to 500. So the rest you don't need to care anymore. The rest you don't need to care anymore. So based on this, you get this result. Get the reading here based on this. Then you just write the answer. All right. So if you want to use 500 to 250 minus the 2 result to get the half-life, also can. As long as you show clearly about your working step. Okay. So you see got 2 marks. Got 2 marks here. So you have to determine the value, show on the graph. That's why you need to show the line. You show the line, so they will accept the answer. So there's nothing to worry. Okay. So and then after that, next question, it will based on the answer here. Based on answer here. Okay. So determine. This one you cannot based on graph anymore. You cannot based on this one. Okay, 1 half-life, 2 half-life, 3 half-life. And then afterwards you get another, okay, another divided half year, and then you get another 4 half-life. So from here you try to study reading, cannot. Definitely cannot, because it wasn't asked you to show on the graph, it asked you to determine. Determine means that you need to do the calculation. All right. So when you do the calculation, this part it become a problem because when you want to show the timeline from 1000, next one to 500, next one to 250, next one to 125, and then next will be the 62.5. So if you don't show the half timeline, it's fine because you can apply the formula. You want to know about ATT after 4 half-life, right? So it's so timeline, the ATT after 4 half-life will be 62.5 pound per what? Per minute. Okay. So then you show the half-life, the timeline like this, you get the answer. So the time 1 mark, the answer is second mark. Or you apply formula also can. But you cannot use a graph lah. You cannot use a graph. Because the graph, it doesn't ask you to determine a time. You just want to know the activities after the half-life. Okay. So that is the question happens on our past year SPM. Okay. So okay, this all you can try to do first. Later on, I will give you the worksheets. But I don't think so. The worksheet I can release before the trial because now I'm starting to create the trial questions already. Right, so maybe I have not enough time to edit all this for you. Okay, to rushing finish the module first. Okay. So this is what I told you in the past year SPM. They may ask you in the objective questions, paper ones. It will ask you like this, to ask you what's A, B, C, something like this. Just only balance the equations lah. Okay. And then the determine half-life, just now we have tried the question. So that's all lah. So the next one is about the nuclear energy. All right. So nowadays you learn very, very little in this nuclear physics. All right. So you see the module I give you, the module I give you, okay, so here there's two questions, 3 questions here. Maybe you can discuss first. Okay, example, the PA take 20.8 hours to shrink from the 80 gram to 5 gram. How many half-life are there? So this one you can use try to use a timeline first. Okay, to see whether from the timeline you can show clear about the numbers of complete half-life. Is on the timeline itself and unable to show that complete half-life, then you have to apply formula. All right. So anyway, I will advise you to avoid the miscalculating. So normally I will advise the student use the timeline method first. Timeline method. All right. Timeline method, it means this is the one timeline method. All right. So from the beginning 80 gram, right? So beginning 80 gram. So 1 half-life divided half become 40. Another half-life divided half become 20. Another half become another half-life 10. So another half-life 5. So from here you can get from 80 to 5. How many half-life? Look at how many arrows they have. 1, 2, 3, 4. So total is 4 half-life. So total you have the 4 half-life. How many half-life are there, right? So but anyway, it gives you the hours here. So this 4 half-life is equal to 20.8 hours. So my question is incomplete here. And then I should ask you how long is a half-life. Okay, so from here, then your half-life will be 20.8 divided 4. So just use the calculator. Okay, you will get 5.2 hours. Okay, 5.2 hours. Right? Okay, so if you apply formula, then how to apply formula if you want to try? Okay, your apply formula will be like this. So the formula given here, this exam will be given in the list. This is the formula. Right, so it means that you have the result is fine, n is fine, and then 1 over 2 power n that you don't know, and then your n naught is 80 gram, n naught is 80. So from here, you have to apply your mx, which is based on the log. Then you will find the n. So by right, you will get the n. It will equal to the 4. N will equal to the 4. You will get the n equal to 4 when you apply the calculations. For those not sure how to do calculate, so it means that you will have 1 over 2 power n is equal to the 5 divided 80. So it's 1 over what? 1 over 1. So use a calculator. 1 divided 4, 80. equal to 0.0625. 0.0625. Okay. So later on, okay, so you have the n will equal to the log 0.0625 divided log 0.5. So it's just use a calculator, right? So log and then divided 0.5 log. So the answer will be 4. You'll get n equal to 4. So for the n equal to 4 already, then n equal to 4, it will equal to the 20.8 divided half-life. Then the other sheet, you will get the half-life will equal to 20.8 divided 4. Just go back to these calculations. So this is how you do when you substitute the formula. All right. So this is the one in the module. Okay, so you don't need to print out, right? So for those that you have no, okay, you can just look at the screen here. Just make your own notes. Okay. So the next one, if given the half-life is 4 days, right? So the giga counter press a 3 meter from the source initially as a count rate 21,600 per minute. After 8 days, so it means that half-life is a 4 day. After 8 days, it means it's 2 half-life. Okay, 2 half-life. So later I will tell you why it mentioned distance 3 meter away. Right. Okay. So from the beginning, 21,600, right? 1 half-life. It will be divided by 2. So it will be the 10800, okay, 10,800, and then another half-life, it will be the 5,400 divided 2. So the answer will be 5,400 count per minute. Okay. So why it mentioned the 3 meter? Actually, there's related to the properties of the radiations, type of radiations decay. So now it's already moved from syllabus. Okay. If you look at the notes here, where is it? Okay, here. I give you here there's a characteristic of the 3 types of the radioactive emissions, which are alpha, beta, and gamma ray. So nowadays it seems like not important anymore in the syllabus, but I think it's better you still learn. Okay, so here's an example about how it's affected by the electric field on the this ligand. And the next ligand, how it's affected by the magnetic field. So because of the alpha particle actually is a positively charged because of 4,2 helium. Right, positive charge, so that's why it was attracted to towards the negative plate, right? So that's what happened to alpha particle. And then beta particles negatively charged electrons, so that's why attracted to a positive plate. So, but why the diffractions beta will be greater than the alpha? Alpha just only slightly diffracted, so that's why it's not immediately bent towards the negative plate. Not because of the alpha move faster. It's this one because of the alpha particle is bigger in mass and bigger in inertia. So that's why when the moment negative plate attract the alpha particle, because of its greater inertia and the momentum due to the bigger mass, so that's why it will be slightly deflected towards it. But the beta particle is lighter, okay, so that's why inertia is less, momentum is less. So once it's attracted by the positive plate, it will be strongly deflected towards it. Okay, and then gamma is a neutral, so that's why it doesn't affected by the electric field. And then for the magnetic field itself, you have to apply the Fleming left-hand rule. Fleming left-hand rule. This one last lesson I already mentioned. Just let me repeat again. When you apply the Fleming left-hand rule, try to be alert. When you point towards for the alpha particle, our direction of the currents in our middle finger, we follow alpha particle. Because alpha particle is a positive charge, so the direction is same as the current direction. So then we just follow it. But when you want to determine the beta particle directions, so the currents, when you apply the Fleming left-hand rule, our middle finger is pointing towards the direction of currents. So in this case, it will be opposite directions. compared to the beta particle. So beta particle is negatively charged, so it means that it's an electron move from backward to the left to the right in the diagram like this. So when we apply the Fleming left-hand rule, our middle finger will be point opposite way from the right to left. Okay, because our current opposite compared to the direction of the electrons flow. All right, so this is only thing that you have to alert lah. Okay, and then the alpha ray, gamma ray is doesn't have charge, so it's neutral. That's why it doesn't affected by the magnetic field also. All right. Okay, just about the detector 3 meter away detect. Okay, actually it is depends on the type of the radiations. Okay, alpha particle is very strong ionizing power. Alpha particle very strong ionizing power, and it only able to move few centimeter range in the air. It can't travel through the long distance. It can't propagate to long distance. So when the alpha particle dig from our radiative source, right? So you can say that it's not that dangerous because it's only can travel in few centimeter. After that, the energy will disappear already. It will be due to is because of the high ionizing power. It will ionize by the air molecule. And anyway, the penetrating power of the alpha particle also very weak. It can be blocked by the piece of tissue paper. So it means that, let's say example someone holding a gun is an alpha particle gun. He said that you do move, I will shoot you. This is a new design of the alpha particle. I will shoot you with the radiative radiation. If you know there's alpha particle going to release from the gun, you don't need to worry. Because first one, it only can travel a few centimeters. When you keep the distance away, you're safe. Second, our skin itself able to protect us because alpha particle unable to penetrate through our skin. It can be blocked by the skin itself, unless it point to your eyes. It then point to your eyes, so our eyes is not strong enough to block the penetration of the alpha particle. If the skin, then it was safe, right? So don't need worry about that. Okay, and then the beta particle slightly stronger. It can travel few meters, and it can be blocked by the minimum required is a few millimeters of aluminum. So aluminum foil, it can block beta particle. Right? But the piece of tissue paper cannot. Piece of this tissue paper, it will penetrate through by the beta particle. Okay. But it doesn't mean that paper cannot block. If you have a thick paper, it still can block. For example, if you have a reference book of the physics reference book, it still can block the beta particle, right? Or the gamma ray one. It's just a concept like the bullet Bullet is very dangerous, right? But if you have the thick paper, it still can block the bullet penetrate through, right? So this is a concept because of the energy of that radiation itself limited. Okay. But the more dangerous one is the gamma ray. So actually we have to prevent the gamma ray leakage from our container to keep the radioactive source. Gamma ray is the one dangerous one because gamma ray have a strong penetrating power. It only can be blocked by the few centimeters of the dip in the concrete. So that's why for our radiative source, we have to keep inside at least we have to keep inside the container made by the dip or the concrete, right? So only that we can try to prevent the penetrations of the radiations. Okay, and then one more thing you have to understand is the radiation itself actually is not dangerous, right? So the dangerous one is a source. Just like there's one question I always ask the students: if there's a glass of water, I have put in front the radiation, gamma radiations. There's a gamma radiation pass through this glass of water. Is that the glass of water still safe to be drinks or not? Many students will say cannot bring anymore because there is a have been exposed to the gamma radiations. Then I want to ask you, have you went for taking the X-rays before? You let the X-ray pass through your body already. Is your body, if you become X-ray woman? No, right? Right. So you still as a normal people, right? Right. The concept is still the same thing. As long as the food, the object itself, have no any dust of the radiative source, even if have exposed to the any radiation before, there is a moment that exposed to radiation. After that, no more. As long as there is no any dust of the radiative sources content inside or out on the surface of the object itself. Because once you have the source there, the source itself will be keep releasing this radiation. That is a dangerous one, right? So that's why that what happened in the Japan now. Japan releasing the radioactive water, which is inside contents of the radiative source, right? The problem is the source when it releasing the radiations is that radiation over the dose can be accepted or not. So even it makes it how we say that like dews is like dews, is it? Like dews with a lot of water. But the problem is if that dose content is over the percentage can be accepted based on the current medical research, then it will become dangerous. The problem is this is based on the current medical research. Our humans understanding about the radiation is still within limited. So for the long-term effect, we still don't know because normally this kind of the radioisotope that in our nuclear reactor, it has a very long half-life. That is a problem. Even a single salt or a single dust go into our body, it cannot expel by our kidneys or our body itself. It will keep inside our body. Then, due to the long half-life, during this long half-life, it will still remaining the same mass. And then it will keep releasing the radiations. The radiation is the releasing of energy. It will cause our health problems, leukemia, cancer, right? Which is we still lack of the data to prove how many dose actually is the safe. We still don't know actually. That is based on the current result. All right. So anyway, what we can do is we have no choice. All right. So what we can do is so hopefully our government try to monitor for us lah. Or unless it's just like the people from China, you buying the ones GM tube. So every time before eat, you try to scan, see how much the dose lah. So they make sure it's safe to eat lah. Right? But if you really scan, you will notice that the reading will be sometimes the reading will be higher than what you're expecting. All right. So later on, you're not going to eat any food anymore. Right? Okay. So this is about the properties. Okay, and then the number S here, this is you use this one I leave it to you and try to do. Okay, for this one in my module, the use of the half-life. Okay, so nowadays they are not really discuss about this one anymore. Just you make it as a part of the general knowledge for you to learn. Okay, so sometimes in our application we're looking for something that long half-life. Sometimes looking for the short half-life. Okay, so example, if you want to use it as a tracer, the example, this is what you learn in chemistry and biology also, technetium-99 as a tracer. So in this case, we're going to inject to the patient body as a tracer. So in that case, we're choosing for the suitable half-life. Normally is example, we're looking for a short half-life. So short half-life, let's say like this one, after 1 day, it will be only left 6.25% after 1 day. So how long is how many hours of this half-life actually? So it means that for 100%, you go through one half-life will become 50%. Another half-life will be 25%. Another half-life will be 12.5%. So another half-life will be 6.25. So it means that 1, 2, 3, 4, 4 half-life. So 4 half-life for 1 day, 24 hours. So it means that 1 half-life will be 6 hours. So this have a short half-life is a 6 hours. So after 1 day, it's only remaining 6.25 in our body, in the patient body. So, but we still need the first half-life so that when inject to patient body, so with this 6 hour, within this 6 hour, we can, based on the radiation detected by our scanner, right? So we're able to know, okay, whether there is we can detect example that they want to know whether your left and right kidney is still function normally. When it function normally, it means that by right you can be expelled out from the body after a day. So if after after 6 hours after 6 hours when you read scan from the machine, notice that there's a one kidney still remaining high percentage of the radiation's activities. Because we still, after 6 hours, there's still 50% remaining in our body. Okay. But when the kidney is able to process, it will expel more out from our body after 6 hours. Then, when we scan, we notice that the reading is lower than 50%, expecting. So it means that your kidney is still function normally. But if you after scan notice that one kidney showing the radioactive tracer that we inject into it is still showing that high reading can be detected, so it means that the kidney is not functioning. So this is one of the way how they detect the problems as a tracer. Okay, and then the small alarm system is usually that we have in our building. Okay, for the because the smoke contains of the alpha particles. So when the so enter the alarm, the alpha particle will be absorbed. So with that, it will be it will make the sound buzzer on. So in the case, our sample to analyze the particle, I mean alpha particle here. So it should be the long half-life, so that we not need to replace the new this radioisotope. Okay, once we install already, then we have a low maintenance. If you imagine that if you take the half-life, let's say a few years, that means that after the one certain period, example, maybe after 20 years, 10 years, then you need to allocate another big budgets to replace all the radioisotopes in this all the small alarm. Then you waste a lot of money, right? So that's why in the case they will choose a suitable half-life, so they have a low maintenance to save the cost. So there's the meaning of the radioisotope. Because the isotope, as you know, okay, there will be the same numbers of the protons, have the different numbers of neutrons. Right. So when they have the same number of protons, means their physical properties are different, right? So one of physical property different means that they have a different half-life. Means that they have a different half-life. Okay. So when they have the same numbers of the because the isotope, so they will have the same chemical properties. Chemical property means that when there is releasing the alpha particle, so it will same releasing alpha particle. Only have the different half-life because of their different physical properties. Okay, so that's why we need to know about the radioisotope, so that we can have the options by the sample that can release the same radiation that we need in our applications, but have a different half-life, depends on the use. Okay, so all this is a knowledge for you to know about the use of the radioisotope in our industrial, in our daily life. So I don't want to discuss so much on this. You can try to read, because this is no longer in your syllabus. Your syllabus now is basically focused on the first one. Okay, for the D6.1, the first thing you have to focus is the three type of radiations, how you balance the equations on the alpha beta decay. Okay, this one we already discussed before this. Okay, and then second one is about the half-life, calculation about the half-life. Okay, and then the formula and the graph. Okay, so that is two main part in your 6.1. Okay, so now if everything okay, then we proceed to 6.2. If yes, please raise up your hand. All right, thank you. Okay, 6.2, basically you need to know the two important process, okay, about the nuclear energy process. How is the radioactive able to release the nuclear energy? Okay, so if you look at your textbook, okay, nuclear energy is what? Nuclear energy is the atomic energy which is released used during the nuclear reactions. The nuclear reaction includes what? Nuclear reaction included what we have learned in the 6.1, which is the radioactive decay, alpha, beta, and gamma decay. And this we already have go through in the 6.1. And then the specific in this 6.2 you're going to learn is another two different process of the nuclear reactions here, radiation here, which is the nuclear fission and the nuclear fusion, fission and fusion. All right. Okay. So look at the nuclear fission first. Okay, nuclear fission is the nuclear reactions when a heavier nucleus split into two or more lighter nuclei, while releasing large amounts of energy. Okay, so this is a process we use in our nuclear reactor. Okay, nuclear reactor they're using here is the chain radiations. So before we learn about chain radiations, we look at the what is meant by the nuclear fission, which is for the one heavier nucleus split into two or more lighter nuclei. So look at here. We have originally we have the uranium-235. Uranium-235 itself is a radioactive, which is an unstable nucleus. So uranium-235 itself, it will take longer time. If I have a long half-life. In this, if you go to the previous example here. So yeah. So this is another sample of the uranium. This one is the uranium-238. This is uranium-238. So means that uranium-235 actually isotope of the uranium, right? So that's why I call uranium. All right. So yeah. Okay. So uranium-235 itself, it will just go through the long half-life until it becomes stable. But it's not going to split into two. It's not going to split into two. Only split into two is the isotope of the uranium-236. Which is when the moment that uranium-235 had been bombarded by the slow-moving neutron. Bombarded by the slow-moving neutron. Okay. This textbook doesn't highlight about that slow-moving neutron, but the concept is a slow-moving neutron. Okay. Then after that, it becomes isotope uranium-236. This isotope uranium-236, it becomes very unstable. Then it was split into two. Split into two lighter nuclei plus a 3 neutron. So here, the equation given in the textbook is one of the example. One of the example. Same as a module that I give you. Right. So there's an example of the nuclear fission here. So same example given. Okay. And so this is process we call it uranium nuclear fission. Okay, and why it must be the slow-moving neutron bombarded by the slow-moving neutrons? Why it's not the fast-moving neutron? In your limitations of SPM syllabus, you don't need to know why. You just need to know how. Okay, how to make uranium can be split into two. You have to be bombarded by slow-moving neutron. That's all. Okay. So and then I tell students you can make a story like this lah. When there's a one family uranium 235, this family is very big. Once big, then become not stable. They every day fighting, arguing between the family member. Okay. So, but it's still remaining as a one family. And until one day there is a one little tree, okay, come in slowly, join the family. Because of that, husband and wife divorce. Okay, so divorce split into two different families now, and then these two different families because the family member too many, so the husband just only want a part of the kids, wife also want a part of kids, and then end up there's a three kids have been just left in the loose side. Right, so this tree is a three neutron, and this three neutron, what happens? This three neutron, because of this bad experience, this three neutron also become the little tree. Then it go and continue bombard. Okay, we're talking about the radio chain radiations here. I don't know why it's split so far away. Okay, the process here is this one. Just now we discussed about the nuclear fission. Here, this is the nuclear fission process. So, and then from the one nuclear fission process, the three neutron, it will continue bombard with the remaining uranium-235. So then it will become another, from one nuclear fission become three nuclear fissions. So this is for the first generation. And then from this, one become three, three will become 9 for the next generation. And the 9 become 27. 27 become multiply 3 again, so become 70. 27 multiplied 3 becomes 71. 81. 81 become 81. So, and then continue for next generation. So it means that this thing happens in a very short periods. 1 become 3, 3 become 9, 9, 9 become 27, 27 become 81. So until the mass original uranium-235 that we demand, no more. Less than critical mass. So if the mass still more than critical mass of the uranium-235 that we have, it will still continue these chain radiations. And then remember, each nuclear fission itself, it will release big amount of energy for each nuclear fission itself. In the chain radiation, can you imagine how much energy have been released? And all this energy is converted as a heat energy. So this is how they use it, control it in our nuclear reactor. So that this energy can be used to heat up the water. Then water turns as a steam. So the steam will be used to rotate the turbine. And rotate the turbine, then it will be generated. We will rotate our generator. So that's what you learn in the chapter 3.5, chapter 5 before this about the chapter 4 about the generator. We need the rotation force so that we only can generate the electricity. So this rotation force is coming from the steam. Come from the steam. So and then the steam, we need the steam by the boiling water. We need to boil the water. When we need to boil water, we need the heat energy. And this heat energy coming from this chain radiations nuclear energy. That's the concept. In the hydroelectricity, our rotation force coming from where? Rotation energy, the rotating force is coming from the water fall down. We turn the gravitational potential energy of the water in our dam. Okay, so when the water fall down, the gravitational potential energy changes as the kinetic energy of the water, and then the water when it hit the turbine, it will rotate the turbine. Right, so that is a process how we generate electricity. So, but in the nuclear reaction itself, our energy convert is from the nuclear energy. All right, so this is concept. We haven't got into the calculation part yet. There is one of the process, we call it nuclear fission. And the second here, we have the nuclear fusion. Nuclear fusion is different with just now. Just now is one big and heavy radioisotope, a stable nucleus, split into two lighter by releasing the 3 neutrons at the same time. But the nuclear fusion is a combine, which is we have the small and light nuclei fused to form a heavier nucleus. Right? Okay, so to form the heavier nucleus, and then it will release the large amount of energy. And this energy compared to the nuclear fission itself, this one is much more higher. But the problem is to combine the two lighter nuclei or to fuse the two lighter, they don't say combine, they use a fuse here. It actually means a combine. Right? So to form a one heavier nucleus, this process needs under the extremely high temperature and pressure to fuse the two lighter nuclei together. Okay. If you watch the movie Spider-Man, if you know about the Dr. Octopus, which is the Spider-Man 2, if I'm not wrong, the Dr. Octopus tried to create the one's new energy source, which is create the one man stun. So there's a concept that it combines two lighter nuclei. Okay, so that's only happened in the movie. And then even in the Iron Man story also said, Iron Man 2, I think Iron Man 2 also. Okay. He tried to create a new energy source by accelerating the particle with a particle collide each other. There's a moment form the new energy source. Right, so this is a concept about the nuclear fusion also. But practically, it's not like the movie, right? Practically, until now, we still don't have the technology to make these nuclear fusions can be applied in our industry. So I heard there's one report, there's one university that already nearly to success about this nuclear fusion, but somehow because of really a lot of the unstable factors, and we don't know when it really happens, what happens. Is it we're going to spoil, we're going to blows our Earth or not? Is it going to become uncontrollable, become the one really like the sun that happened in the Spider-Man 2, lost control? Then what happened? So nobody's know. Only know that with the current technology, with the limitation of the knowledge about this, so we're still unable to make it become reality and apply in our industry. If we can if we can apply this, so it will be another new energy source. Okay. So this is based on theory, but anyway, is it this thing happens or not? Yes, it happened. Where is it? It happened on the surface of our sun. So the sun, that's why the sun had able to release a lot of energy, right? So this happened on the surface of the sun. Okay, all this energy release is because of what? All this energy release is because of the mass effect. What's my mass effect here? So we look at the equation here. Okay, so uranium-235 have its own mass. Neutron also have its own mass. After the neutrons, slow-moving neutron bombarded with the uranium-235, then there's a total mass initially that we have. So once it becomes uranium-236, it was split into two. Then these two lighter nuclei have its own mass plus the 3 neutron. So there will be the mass initially that we have. We have the mass after the nuclear fission process. So when we minus it, so we notice there is a loss of mass. So it means the total mass that we have after the process, the nuclear reaction process here, we have mass loss. And this loss of mass, we call it mass defect. And this mass defect is turned as energy with formula E equal to mc squared. M is the one that I said, mass defect, which is original mass minus the mass after the process that you still have. So this is the M that we substitute in the formula, mass defect. So multiply with the C squared. So this is our energy. So E equal to mc squared is the famous formula that we have. Okay. Same also for the nuclear fusion. Even we have the two lighter nuclei before, but these two lighter nuclei, their total mass is still more than the heavier nucleus mass after the nuclear fusion process plus a neutron. So it will be still more. When we minus it, we still have a loss of mass. So this loss of mass is the one we call mass defect. Right? Okay. And the mass defect itself. Sorry, yeah. So the mass, if the mass defect itself, okay, here, it will be given in the unit that we call it atomic mass unit. Right? During the exam, will give you as atomic mass unit, AMU. So 1 AMU is equal to 1.66 times 10 to the power negative 27 kilogram. And this will be given during the exam. Yeah. So this is 1 AMU equal to 1.66 times 10 to the power negative 27 kilogram. So what you need to do is you need to find that mass effect in AMU first, then only the final you get the how much mass effect in AMU already, then only convert it into a kilogram by multiply 1.66 times 10 to the power of negative 27. You don't need to change each one, the MU here into the kilogram, into kilogram, into kilogram, into kilogram. Those do so much convert. No need. Right. Everything here, you total it based on the MU. Once you get the MU is how much your mass effect already in MU, then only you convert it into a kilogram. So then remember, please remember, before you get the final answer of the energy in unit joule, please do not round off the value. Do not keep from the original 4 or 5 decimal and then only keep 3 or 2. Make your calculation simple. Don't do so, because it will make your final result have a big difference. Whatever decimal that you get from the original value, you keep it until your final answer, then only you decided want to keep less decimal or not. No matter how, remember, this is very small value. There will be a lot of decimal. So please keep your final answer at least 3 decimal places. At least 3 decimal places. Don't keep 2. For the answer, original answer by calculator, if more decimal places, make sure you deduce it, at least keep 3. Keep 3 decimal places. Right? So even that is in the standard form, still keep 3 decimal places at least. Right? So here's the process how we change the 1 MU into the unit kilogram. Actually, this is something like more to like chemistry. Okay, so you learn in chemistry actually. So I don't want to discuss so much on this. Okay, so later on we have time, then we only go through that. So because in exam, I don't think so will ask you going to prove this unless you are in the A level or foundation. They'll ask you to do so. Because in exam, we just need you to apply how to change MU into kilogram and substitute the formula equal to mc squared to find the answer for the energy. Remember, this question we must score because E equal to mc squared. There's only 2 possibilities they can design the questions. Either it asks you to determine how much energy, or either it gives you the energies already, it asks you to determine mass defect. That's all. They got no any other possibility. Because C is a constant value, speed of light in vacuum. 3 times 10 power 8 meter per second. And then usually exam, the students still calculate wrongly because they've forgotten there's a c squared. They always forgotten there's a c squared. So make sure it's a 3 times 10 power 8 squared. So it means you are multiplying 9 times 10 to the power of 16. But many students, I don't know why you always calculate wrongly. So please learn how to use calculator, girls. Please, I hope there's no one calculate wrongly in the coming trial for this one. I already remind you, okay? Okay, so here's an example in the module. So later when I give you the copy, then only you answer it. All right. Okay, so see anything else you need to know. Okay, so you see the calculation part here, example in textbook. All right, so this you see when you determine the mass effect, so everything decimal all you keep. Once you get the MUs already, we substitute to formula MC squared, then only you change the M to the unit kilogram. Then after that, substitute. So you see, still keep 3 decimal. After multiply already, so I'm not sure whether there is another decimal here or not. You do try to do calculation. If there's another decimal up to 3 decimal, then keep 3 decimal. Don't follow this 2.69. Right. So you do calculate. Try manually calculate. See how. Use a calculator. See is it the 2.69 is the final answer or there's a number after the 9. So I'm not very sure. Right. If there's a number after the 9, please keep. Show the 3 decimal. Right. So I think this part is done about these 2 different processes. So in your textbook, I think it's also made the conclusions for you. The comparison between these 2 processes. Let me see it's have or not. Last time macam ada, I've forgotten already. Oh, it doesn't show you. So anyway, in my model, I give you. Right? So the difference between the nuclear fusion and nuclear fission. Right? So don't be confused about the terms. All right. So after this process, okay, and then remember which one will be able to release more energy actually is a nuclear fusion. Because of that our technology is still not able to support to make reality. Right, so we cannot invent the machine to have this nuclear fusion. So currently, this nuclear fusion, we only able to say that it's difficult to control. Actually, we still unable to control it. All right, so it only happens on the suns, okay, process of how to power the suns. Okay, so the next you're going to learn is a basic concept about the nuclear reactor, so that you know what is meant by nuclear reactor. So how to say? Actually, this knowledge here, you will notice that it will try to convince you, right? Nuclear reactor actually is better options to generate electricity, which is not harm to the environment. Is even the energy even green than hydroelectric power. Okay, you see, where is it? Yeah. The use of a nuclear energy as an alternative source to generate electrical energy. Right? You know why? Okay. If we really can control knowing how to manage the waste management is very important. The radioactive waste management. Right. The way how we use the energy to generate the electricity, the nuclear energy, is really lower cost and high efficiency compared to the dam with hydroelectric, hydro dam in the generate electricity. Nuclear reactor is really much higher efficiency. Okay. The main problem is the waste management, just like happened in Japan. All right. So once they have any accidents, so the question is, are we have enough knowledge and technology to handle this? That is the questions. As usual, you will see that a lot of people will tell you, don't worry, we will always use the latest technology. So for me, I don't know where is the latest technology come from. If they really have the latest technology safer, why they don't apply on the current nuclear reactor? Is it because they have no money to change the designs? I don't know. Because this part is too complicated for us to know. Okay, so anyway, if you search on internet, there's a lot of different design of the nuclear reactor implement in the few countries that have a nuclear reactor. But if I'm not wrong, actually the United Nations, they have one agreement. It seems like they are hopefully they're hoping there's no any increments of the numbers of the nuclear reactor. Right. But the problem, the country is already on the nuclear reactor. They are still building the same new nuclear reactor. Right. So sometimes political realities difference. All right. So this is something that out of our control. Okay. So, but one thing for sure, if any politicians try to convince you, say that don't worry, our nuclear reactor is safe. Our Malaysia, we have no natural disaster like the earthquakes or the typhoons or whatever. We are more safe compared to the country like others, right? So as you study the geography, say that Malaysia got no earthquake problem. You tell the Sabah people, say the Sabah people still believe that. The Sabah is already reported a few times of the earthquake, right? It's still for sure it's safe. I don't know. Okay, so there is the problem of the next generations. Hopefully that. Okay, if I always tell students if there's any politician told you so, don't worry, it's safe. We will use the latest technology. Okay, then if really there's a thought right in front of me, so I think I'll raise up my hand to tell to tell the politician. I say yes, I agree with you. I totally agree with you. It's safe. We will use the new technology. So why not the nuclear reactor built next to your house? Right? Or you move your house next to a nuclear reactor. If you agree with that, then I totally agree with you. Okay. So, right. Okay. All right. So have a look for this nuclear reactor. Look at the simple process here, as I mentioned just now. Our reactor is here on the number one here. So this is our nuclear reactor. So inside, the energy will be used to heat up the water. Water will boil. When the water is boiled, then it will turn into steam. So the steam will go to the steam will flow through and then rotate the turbine. Rotate turbine already, it will be condensed. It will be cooled down. So once it cool down already, so that's why it will be turned back as a liquid and then go back and repeat the cycle. So that's why for cool down this steam to condense back the steam back to the liquid, we need the cooling tower. So this cooling tower have a running water, so they can remove the heat to the surrounding. And then you see that it's always there's a steam came out. Because the process one for the condensation process, we have to remove the heat from the steam so the steam will condense back as a liquid. So this due to that, normally all the nuclear reactor they will build next to the source of water. Usually they build at the seaside because you're going to use the seawater, okay, as a source of the water for this cooling tower. Or if they have no suitable locations, then they will build it at the in the middle land, right? So the kill away from the city, no really far away, okay. and after they will have the pilings to supply the water. Okay, so there will be have an additional cost. And then it cannot be very far away from the city, because if far away, then you will still have a problem for the cable transmits the electricity. Okay, anyway, there's a lot of water for this nuclear reactor. So usually the nearby of the nuclear reactor itself is the one small town, because all the water will be stay nearby. So it's also will be increased as the opportunity to have the people have the works. Okay. So that's why the anyway they will be very important for the country economies. Right. So if you want to continue build the country, you have no choice for that. Okay. In this nuclear reactor, right? So we have the control root and the moderator. So moderator is to slow down the fast-moving neutron, as I told you, because we need to have a neutron slow-moving neutron bombard with our uranium-235 to form the isotope uranium-236. Then only the nuclear fission can be occurred. And these nuclear fissions that we have, and with the uranium-235, that we have the critical mass more than that, then you will be occur the chain reactions. The chain reaction is the one that release energy to boil the water. Okay, and the control root is the one that we use it made by the borons or the cadmium, so that is used to absorb the excess of neutron. Because if there's no more neutron, then they're not going to bombard with our uranium-235. Then there will be no nuclear fissions occur. When there's no nuclear fissions occur, so there will be no release, there will be no chain reactions. Then will be not going to release the nuclear energy. So that's why when the moment they want to shut down or they want to control the rate of the energy release, so they will use the control root. Okay, so when the control root is totally go down, slot into this monitor, or go into the uranium root here when it's going down, so it will totally shut down the nuclear reactor, because once the control root is going down, then means that you're going to absorb all the neutron. Then will be shut down the reactor. When you lift it up, so it will be fully nuclear reactor will be fully working. So it will be come to optimum energy to generate the electricity. All right, so this is the control root very important. Okay, so I think that's all for our this chapter. Okay, so basically the last part here about the nuclear reactor, you have to read whatever status in your textbook to know all the functions, moderator, control room made by what, and then why we need the thick concrete wall, so that it preventing the dickings or the leakage of the nuclear radiations, right? So it must be fully sealed, so that preventing the releasing of the our radioactive dust into the air, right? So it must be a thick concrete wall, so that it preventing especially the gamma ray penetrate throughout to the surrounding. Okay, so and then the water as a cooling agent, so that condense back the steam, so the process can be repeated. So all this you read to know when the question asks, that's all. This is the one that you're going to give. When the question asks, exactly this is what you read, what you answer. Okay, I think there's no more. So let me repeat again. Make sure that you know what's the nuclear fissions and how to have the chain radiations. I think I mentioned clearly in my module. To make the chain reaction to occur, we need the minimum mass of the uranium-235 that we call critical mass. How much the critical mass, we don't know, right? So we only given the knowledge in the limitations that as syllabus here is, as long as it reaches the minimum mass, then the chain reaction will be occurred. It doesn't have this minimum mass, so the chain reaction is not going to occur. Okay, so when it's a loss control, actually that is how the atomic bomb explosions. If we can control it, then with the number of neutron that bombard with the unitrify, so we can control the energy release. If we lost control, then the giga, okay, so the large amounts of the energy will be the release at a short moment, short time, so it will burn everything lah. So this is about the atomic bomb lah. All right. And then after that is a nuclear fusion process. Nuclear fusion process, at least this example, 3 example I given in my module. At least you try to memorize one. At least try to memorize one. So this, I think this is given in the textbook. Is it? Or this was given a different one? So this example given in textbook. Okay, for the to form the one alpha particles here, O2 helium, right? So at least you get to know one example. So in case it asks you write an example for the nuclear fusion process. It happened in past year for 1 year. Ask the student write examples of the nuclear fusion process. Right. So that's why I advise you to at least memorize one of the example equations here, and also for the nuclear fission process, also same. So this nuclear fission process, this one you try to memorize also for this example. All right. So just only memorize one each one for the each process here. Okay. So I think that's all. We finished our chapter 6. Okay. So is there any specific questions? If not, then tonight we just finish like this. We done our chapter 6. So about the chapter 7, later I will arrange another class. Another 2 more lessons, I think we can finish chapter 7. And chapter 4, chapter 5 electronic. So I will finish at the school, right? So as I told you, I can finish the syllabus before the trial. So if for the moment got no any question, then that's all. Good night. So we finish our class. Thank you.
Thank you, teacher.